Um, Let me also say that I have decided to the office hours on Tuesdays. Office hours on Tuesdays at, well, between 13 and 14. Okay. So as a result, I'm going to start with today. So I'm going to be on the, on this channel on Zoom. So if you just log into online classes, then I'll be there, right? I'll be there. I'll be just waiting. So as a result, if you want to ask anything, then we can talk there, right? Just keep this in mind. What else? So yeah, we were actually talking about this Coulomb's law, and then we have said lots of different things. So let's just say it like this, all right? So first, we have said something about the force between two charges with a distance. R is the distance between them, and the force applied on this charge Q2 is, well, first we define this unit vector. That's basically the unit vector that's for the vector pointing from 1 to 2 actually. So let me actually show it like that. So then we have said that the force on 2 is equal to, that's 1/4 pi epsilon 0 Q1 Q2 divided by R squared times the R unit vector. So that's the Coulomb's law, but expressed in a mathematically, I mean, for you, complicated way, but I mean, with this mathematical expression, of course, there are some certain simplifying features as well. So in that case, we don't even have to worry about the sign of the charges. And then we have said that, just forget about this, we have said, I have said that if there's a charge Q2 in here, and then there's also an electric field in here, right? And we have said that in that case, the force on the charge can be written as the charge multiplied with the electric field. So that's basically the force applied on, right? Applied on, let's say, particle with charge. Particle with charge by electric field. So that's essentially is field. We have said that, well, it's not actually, it's not possible for two charges to directly interact with each other. Actually, the charge is interacting with the field itself, the electric field. And what's the nature of that interaction? First of all, the electric field applies a force on charged particles. I shouldn't actually say charge, but somehow we get used to this idea. Charge is basically that property of the particle. So it's a force applied on the particle. Charge is just a property. It's like the mass, or I don't know, some other properties of particles. I don't know what else are there. So it's basically a quantity, a number that actually tells us how strongly this particle interacts with the electric field. Okay, so do not think of the charge itself as an independent physical entity. It's just the properties of particles. So it's the force applied on a particle by the electric field, right? And then we have said that, charges produce electric fields. So this charge in here is going to produce an electric field at that point, which is at a distance r from the charge itself. Let me also use, let me also use a white color to show the radial unit vector. In that case, the electric field produced by that charge, or perhaps I should say modified, but in any case, the other charges may also produce or contribute to the electric field. but it's that a contribution of that particular charge. In any case, so there are these two aspects of the interaction between the field and the charge. So charges produce an electric field, and electric fields apply a force on particles. Sorry, particles produce an electric field applies forces on particles. And charge is basically the coupling constant of how strong that interaction is. Okay, so that was the explanation that we have provided. So we have said that, well, this solves this action at a distance problem. We say that two particles do not interact directly, so their interaction is mediated by this electric field. And in any case, so there is a physical entity called the electric field. It's not matter, so therefore it is hard to imagine about them, but there is no doubt about their existence, right? This is kind of a summary of what we have said the last time. So from now on, we will be talking about the electric fields. And well, this part is easy. Force applied by the electric field on charges. This is always in that form, right? But most of the time we will be talking about this feature in here, how charges produce the electric field. Well, that's also easy, right? That's the Coulomb's law, basically. It's the modified form of Coulomb's law. So this time we're not talking about the force, but we're talking about the field produced by the charges. And then we have talked about the electric field lines for visualizing these fields. All right, and then the next thing is, I mean, I've just prepared some offline video for this and probably, you know, some introductory parts, but basically the idea is how can we compute basically the electric field produced by a continuous charge distribution. So for point charges, it's easy. It's basically the superposition principle. So basically, if this charge produces an electric field in here, let me write it down like that. If, let's say, E1 is the electric field produced by this charge, and E2 is the electric field produced by that charge, I'm just drawing these symbolically, E2. Then together they are going to produce an electric field, which is just the vector sum of these two. So this E1 plus E2 will be the total electric charge, total electric field, sorry, produced at that point. So if we just have different particles, it's easy to compute the electric field. What if there is a continuous charge distribution? So, for example, a sphere, yeah, or I don't know, any irregular shape like that. So there should be some kind of a description of this charge distribution as well. We are going to talk about this is the charge density, basically. We will also ways of describing this. And we would like to compute the electric field produced at some other given point. So what's the electric field produced by all of these charges in here? And somehow I should be able to compute the electric field produced by each one of them and then add them up. So the situation is something like this. I don't know. I mean, this charge, for example, produces an electric field somewhere in here. This charge produces an electric field somewhere in here. So there are many small electric fields produced, and somehow I have to integrate them. Okay, so the idea in here is that what we do is we just divide this continuous charge distribution into small pieces. So we just call the charge on each small piece as dq, and the electric field produced by this charge right at that point would be usually denoted by dE. So that's DE. Let me erase this, this part of the expression, actually, right? I need to compute their sum, basically. So DE is given by the Coulomb's law by this expression, dq divided by r squared times the r unit vector. So in any case, this is just a contribution coming from a single charge. So I have to integrate over this. Right, let me actually show it like that. And that's going to give me the electric field. I mean, this is the procedure that we have to carry out. Unfortunately, this is just a recipe. Recipe means it tells you how to do the things, right? For example, it's a recipe for a cake, right? It's just a set of instructions to prepare a cake. As a result, this is different from a cake, actually, right? So unfortunately, some people think that this is actually an expression that they can integrate, where Q is a variable and I don't know, the other things are just like that. No, that's not the case. It just contains some instructions. So as a result, there are some things that you need to do in here. Just like you cannot eat a recipe, you can only eat a cake. You shouldn't integrate this. You cannot integrate this. So you, first of all, you have to prepare this integral. And only after that you can integrate, okay? So as a result, so we are going to talk about the examples where how we can prepare such integrals. So there are some certain geometrical details that we will talk about. So there are a few things that you have to notice in here. So that, I mean, we need to find some integration variable. That's one of the things, because in calculus, we always have an integration variable. So we express everything inside in terms of some kind of a variable, and then after that we integrate. So that's one of the things. And the second thing is that this dq in here, the distance r and this r unit vector, they are in principle all variables. They actually may change depending on where you choose this dq charge piece in here. So they are all variables, so you should be able to actually express them in terms of this, your integration variable. Okay, so I'm just going to look at this r unit vector. So that's basically an integral of a vector quantity. I know that most of you are not comfortable with vectors. So for those cases, it's actually quite advisable to look at the components of the vectors and then integrate. So what you need to do is, like, for example, you just compute the x components of the electric field, which is basically given by, again, the same expression, but this time you take the x component of the r unit vector, right? So this is probably some kind of an angle. I don't know, let's say it like cosine theta, for example. I mean, cosine of some kind of an angle, perhaps. But that will be some kind of a component. And then you do the same thing for the y component and so on for the z component, right? This is what we usually do. So let me write this thing down. And the z component and so on. So as a result, you evaluate all of these separately. So as a result, in principle, you have three integrals that you need to compute. In some cases, however, because of some symmetry arguments and things like that, you may know the direction of the electric field already. And so as a result, you may safely say that some of these integrals are already equal to 0. So as a result, you don't have to compute them. So we will be basically seeing only those kind of cases, right? So there will be some situations that you will be able to say that, well, for example, EY and EZ is equal to 0. So as a result, you don't need to worry about this. Okay, so the first example, this is something that I have already solved in these offline videos. So it's basically a thin line with length L. Thin line with let's say it like this, length L, charge Q, and this is uniformly distributed. Yeah, I'm not going to solve it. I somehow happen to remember the solution. So as a result, I'm going to write this thing down. So I think that distance was equal to A, and we were looking for the electric field at that point. Okay, so I'm just going to describe the features in here. So I'm going to use this yellow color. So what we did was we have chosen some kind of a coordinate in here. That's basically the X coordinate. So somehow we parameterized the rod, and then we have chosen some small piece of rod in here. It's this length is equal to dx, whatever. So we have found the charge in here, computed the electric field produced by that charge in here, and then we just noticed that the R unit vector is equal to already the basically this radial unit vector is always the same, no matter where you choose this piece of charge. So as a result, this somehow simplifies. So that's something that's basically it's not a variable. It doesn't depend on the coordinate of the charge that you have chosen in here. So that essentially means that you need to evaluate only this EX integral. So let me write this with white. So you need to evaluate the EX integral. I think I'm going to write this thing down like that. Sorry about this. I think this is L plus A minus X squared. There's this part of the integral, and somehow the EY integral and the EZ integrals were already equal to 0. So these were simple enough. And so as a result, we didn't need to compute these Y and Z components. Only the X components of the electric field was needed to be computed. Okay. So there are a few things that, yeah, I'm not going to solve this problem, but this is actually quite simple in some certain respects. So first of all, we don't have a unit vector which is which depends on where you choose the charge. So that's a simplifying factor. So as a result, let's just go to a problem where there's a dependence in there. So in that case, this is the problem that I'm going to solve. I have a rod, again, a thin rod, but this time it is infinite. Okay, and I'm sorry about this. I need to decide on which variables I have to use. So I'm going to use capital R as the distance of that point to the wire. Usually I choose little r, but I don't want this case to be confused with this demonstration. So that's a infinite line of charge with uniform density. Okay. So we have to say something about the distribution, obviously. So we have to say that it is uniform, and then we have to give some quantities. I would like to give the total charge of the rod, this infinite rod, but unfortunately total charge is infinite. So all I can do is to give the density, right? So I'm going to then define lambda. So that's given actually. Lambda is the charge density on the line. So let's just remember that this is a linear charge density. So that's basically it's the charge divided by length. So the unit is coulombs per meter, basically, in units. So this is also given, lambda. Right, so I mean, there are only two parameters in that problem, the linear charge density and the distance to the wire. Okay, I'm going to solve this problem. This is a little bit long, but I mean, the problem is not that complicated. The integral is very easy to form and then very easy to integrate. But I would like to explain it from the point of view of two possible choice of variables. So as a result, I'm going to start with the Cartesian variable as a variable that describes the location of the charges on the line, and then pass to a different variable. So we are going to see, but the essential idea in here is this. If I choose my charge in here, a piece of charge, in that case, the electric field produced by that piece of charge would be something like that. Sorry, that's gray. So, so this dE would be the electric field produced by that piece of charge. But if I choose my piece of charge in here, in that case, the corresponding dE would be somewhat like that. Right? So as a result, all of the electric fields produced by different charges on the rod are always in different directions. So I can actually think about all the possible electric fields in here. So as a result, they form, I don't know, there's basically an infinitely many infinitesimal vectors, which are all in different directions, and which basically, I mean, I have to add them up. So the essential idea is, of course, that I mean, we have an integral like that of all of these small vectors. Forget about these geometrical ways of adding vectors. It is hopeless to use it in here. But we can do it in the form of an integral, obviously, but for the components. So we are going to integrate the x component of the electric field and the y component of the electric field separately. Right? This is what we need to do. Also, let me also define the x and the y directions like that. Okay. Now, there is actually a fortunate thing in here. There's a symmetry in that problem. So the symmetry is the left-right symmetry. This is something that you see, and so as a result, you intuitively understand what this thing is, what the symmetry is, what are its implications. So let me actually do it like this. So I'm going to, unfortunately, erase everything else in here. Right? I think I'm going to erase everything. So whatever these individual electric fields produced by each individual charges is, we know that the total electric field is always in along this direction. Or it is radially inward, I don't know. It might be also be pointing along that direction if the charge on the rod is negative, obviously. So that's not the thing that we are talking about. But what I'm saying is that the y component of the electric field in here, that's the one that we need to compute. But the x component of the electric field is equal to 0 by symmetry. Right? Because of the symmetry, even though all of these are non-zero, we know somehow that the integral is 0. So as a result, we don't need to compute this. So don't spend any time on computing this, because you already know that if you integrate it correctly, then you would get 0. So why waste time? And so as a result, there's only one integral that we have to evaluate in here. Okay. So I'm going to now start formally start solving this problem. Right? In the problem, there are these two parameters. This is the linear charge density of the line, and this distance in here, and we would like to compute the y component of the electric field. I don't know if you have any questions in here. If you have any questions, please ask me. Let me add one more comment in here. I said that the linear line of charge has a uniform density. Uniform means this linear charge density is constant. Okay. The density has the same value everywhere. And non-uniform charge distribution is a distribution where that lambda quantity, the density changes from point to point. So we will also solve some problems with non-uniform charge distribution. Not in that chapter, but in the next chapter. Because, yeah, well, because we can solve these kind of problems. All right. So let me then start with this. So I'm going to draw the rod again. This is infinite rod. So, all right. So I'm just going to draw it with just a single line. All right. So let's do it like that. I mean, it has a thickness, but it is a negligible thickness. So as a result, the thickness is not going to be important in any case. So this is the point in question, and I would like to find the electric field at that point. And let's remember that that distance was r. So what I do is, first of all, I'm going to show this with a different color. I choose my x-axis. I choose my x-axis. So there's a direction to the x-axis, of course. And I'm going to, yeah, I think I'm going to show it like that. So this is the direction of the x-axis. And I'm just going to choose the axis in such a way that it coincides with that physical charge in here. And also I'm going to choose my origin in here. So that's the simplest solution. Okay, so let's just note this. So the charge is between x as a coordinate, x equals minus infinity and x equals plus infinity. So these are going to be my integration boundaries. All right. So these are the boundaries. So x is my integration variable. So let me write this thing down. Right. X is my integration variable. And these are my boundaries, right? But this is something that I'm going to do it only at the end. So what I need to do in here is this. Yeah, the y-axis, I'm going to choose it like that, all right? So let me just draw it somewhere else. So I don't want to make the picture complicated. So what I do is this. I just consider all the charge between the coordinates x and x plus dx. So I'm exaggerating this. So as a result, I'm just going to draw it like that. Okay. So the left point has a coordinate x, and the right coordinate has a coordinate x plus dx. Right? It's the same thing that we have used. So for Cartesian coordinates or for any other coordinates, so I think about the amount of the charge with coordinates that lie on a small infinitesimal interval. So the length therefore in here is dx. So here, dx is infinitesimal. If you want to think about what this means in physical terms, this is smaller than everything, every other length scale. Every other length scale in the problem, right? So it is smaller than x, for example. In any case, at the end, I know that at some point, I'm going to take the limit where this dx goes to 0. let's say it like this, limit is taken when integrating. Okay, so as a result, I mean, mathematically, some limiting procedure is taken. So as a result, what I can do right now is that I just consider this as a very small quantity, smaller than every other length scale. So there are some situations where I'm going to omit that length. In some situations, in some other cases, I don't. So for example, how much charge is there on this line segment in here, on this piece? So I'm going to show this by dq. This is basically given by lambda times dx. So as a result, this is a formula, this is an expression where I cannot omit dx because otherwise I would get 0. So there's a charge in here. It is as small as the length of that segment. So therefore this charge is also an infinitesimal. But just keep in mind that this is not a differential, right? A differential is basically the difference of some kind of a function. I mean, it's some kind of a difference of something. But we sometimes use this D notation to show things which are also infinitesimal, but they don't have any meaning of being a difference of something, right? So dq is just an example. Right? So we just say that this dq is infinitesimal charge. Sorry. So that means when you take the limit dx goes to 0, this also goes to 0. And for all such quantities, I always add a d in front to actually remind us that these are extremely small. Okay, so that's kind of important. And then we have the other things. I think I'm going to go and then draw this picture again. But let me draw this thing in here. So sorry about that. So there's this line in here. So that distance is r. So what we do in these kind of situations is we basically just compute all of these variables. So I know that this distance is x. So from here, I can say that, for example, this r quantity is the square root of x squared plus r squared. Okay. And then I just, sorry. I was always using this blue color. So the electric field produced by that piece of charge in here, right at that point, I first draw it in here. I don't need this electric field vector, but I need its components. So as a result, I basically think about all the components in here. So in any case, I'm just going to draw these two. So there's this y component in here, and there's an x component. So I'm also going to talk about these as well. In any case, there's one more variable that I may need. So I'm going to use this angle theta, which is basically that angle too, to express everything. So I think I'm going to use this picture again. So as a result, let me slide it towards right. Okay, so this is what I do. So first of all, I write the magnitude of the electric field dE. So that's just the magnitude only. So we have dq divided by r squared. It's the magnitude only. I actually need the need to multiply this with the r unit vector in here. There was an r unit vector. In that case, I would put a vector sign in here. But I just, first of all, write down the magnitude because I don't need the vector actually. I need the x and the y components. So the x component is minus 1 over 4 pi epsilon 0 dq over r squared times sine of theta. Why did I put a minus sign? This is basically minus sine theta is the x components of the radial unit vector, right? Let me just write it down like that. So that's the correct answer. That's why I did this. So our x component of the radial unit vector is equal to minus sine theta. That is why I put the minus sign in here, but you can usually write down these kind of expressions with the correct signs by just looking at the picture. So in all of these cases, I'm not really assuming that the charge on the rod is positive. It can actually be negative. If this charge in here is negative, basically the linear charge density is negative. So that means this dq is also negative. In that case, I have a negative number in here. Negative, negative gives you a positive quantity. So that would basically mean that in such a situation, the x component of the electric field would be positive, right? So, but in any case, this equation is consistent with all two possible signs of the charge. So it doesn't matter whether the linear charge density on the rod is negative or positive. In both situations, this formula is valid. And when you integrate this, you are going to obtain a valid expression for both cases. However, when you're writing down this kind of an expression, sometimes people think that, for example, the charge is positive, and then they decide on the signs in here, assuming that the charge is positive. They just write down the formula, and then they notice that at the end, the formula is still valid, even if the charge is negative, okay? So this is the part of the question that you should never worry about. So if you have some difficulty in imagining things, just assume that the charge is positive, just do your derivations, and at the end, check if your result is still meaningful, if your variable charge quantity is negative or not, right? But during the derivations, you can assume that it is positive. No problem with this. I mean, if it makes you comfortable, then that's okay. So in any case, so what's the y component of the electric field? So this is 1 over 4 pi epsilon 0 dq over r squared. That was the magnitude. Y component is this, so that's basically cosine theta. So that essentially means that the radial unit vector has a component which is cosine theta. Okay, I don't know if you have any questions in here. So this is the part that is a little bit complicated. But in any case, so let me then say it in here. I mean, we don't have much space left in here, but I know that at the end, this dx is not 0, but if I integrate this, I know that I'm going to get 0. So as a result, I know what the result is. And so for that reason, I don't worry about writing this thing down and integrating and whatever. So at the end, I know what I'm going to get. So no problem with this. But I need to evaluate this EY integral. And here I need to do some work. Okay, so I'm just going to do it like this. So I'm going to shift this to the left again. So this is the one that I'm worried about. I think I'm going to box this. Right? I need to evaluate this integral, EY. That's 1 over 4 pi epsilon 0. And then we have dq over r squared times cosine theta. Right, that's the one that I need to evaluate, but still it's not in the final form that's ready to be evaluated. This is still symbolic. So there is this dq quantity in here, there is r quantity in here, and then there's this cosine theta. I need to be able to express them in terms of a single variable. So express all in terms of the integration variable. Which is basically x. So I have to write down somehow dq in terms of dx. I need to write down r in terms of x. So we have done this. And I have to write down cosine theta in terms of x. So I need to look at this picture again. Cosine theta is capital R divided by the small r. So let me write this thing down. So capital R divided by small r. So that's capital R divided by the square root of r squared plus x squared. Okay. So, so when do you stop? So when you have an expression where everything in the expression is either the variable, which is x, the variable of integration, or the given constants like r or lambda and things like that. Okay, so this is the final point that where you stop. And well, otherwise, I mean, you should always evaluate this, all of these variables. So I'm again continuing. So we have dq is lambda dx. Lambda is a constant. Sorry. Let me write this thing down like that, right? It is r squared plus x squared to the power 1. Yeah, forget about it. So I'm going to write down 3/2 in here and multiplied with r. Okay, so as a result, this little r appears one more time inside cosine theta. So we have like the 1/r cube appearing there. So as a result, this is the expression. So at this point, inside the expression, I have just the variable x and the other constants. And the other constants are the given constants of the problem. So this is lambda and r. These are constants. I mean, they are not variables. These are just given quantities within the problem. Okay. So as a result, these things do not worry about me, but I mean, there are some other variables that I have written down. I have just used in the derivation, like little r or theta and things like that. I have to make sure that I express all of them in terms of the integration variable. All right, so that's the last stage. The very last stage is, sorry, the thing before the last stage is place the integration boundaries. So that's minus infinity and plus infinity. The charge has coordinates ranging from minus infinity to plus infinity. So therefore, this is the final integral. And then what you need to do is use calculus at that point. So this is the point, the very last step, where the things that you have learned in the calculus course becomes useful, right? So use calculus after that. So this is the part that we don't talk about in our course. So that's something that you have learned in a different course. The part that we are talking about in here is the things that you do when you are preparing this integral, right? This is the part that physicists usually do, right? I mean, take this geometrical picture and yeah, do an analysis on that picture, and then from this picture, you just construct that integral. And to do that, you use lots of different things. You use physical ideas, you use geometry, and actually, this is one of the simplest problems that you can actually do that. In any case, I'm not going to evaluate this integral because I think this is too complicated for our course, but let's just say it like this. You can use change of variable method, right? So in the change of variable method, you just replace the variable of integration with some other variable. And in these kind of situations, you probably have learned in calculus that you have to replace the variable with r times tangent theta. So that simplifies this expression. In any case, if you want to do it like that, go ahead, but I'm not going to solve the problem like that. So, but this is the way that people do. I just noticed that this theta variable in here is the same as this theta quantity that I just used in my geometric picture. So this tells me that probably I could have prepared this integral in terms of the variable theta from the beginning. Okay, so instead of doing the substitution at the very end, I could do the substitution at the very beginning. All right. So this is what we usually do. So it appears that for this infinite line problems with uniform charge density, infinite line problems, theta appears to be the natural variable that kind of gives you simple integrals, right? And so as a result, it's important that we actually start from the beginning, do everything that we have done up to this point, but this time use the theta as the variable. Okay, so in the second hour after the break, I'm going to do this. So this part of the solution will be actually a little bit easier. So in a way, I'm actually going to repeat the steps that we have taken. Okay, so let me stop here, stop the recording.